All right, yeah. Hi, my name is Mark, and this is the final presentation for the algorithms for fair and unbiased redistricting. So our team sought to tackle the gerrymandering problem, which, if you're not familiar, is basically the manipulation of district boundaries to give a political party an advantage in congressional appointment. So this generally takes two different forms, cracking and packing. Cracking is when you take a group of one type of voter and break them up into a lot of different districts so they can't actually get a majority and thus do not have their votes count. And packing is when you take a bunch of people of one particular political affiliation and put them into one district so they have a hypermajority and thus they have a lot of excessive wasted votes. This is pretty well depicted in this right diagram over here, which we grabbed from the Washington Post. As you can see, we have a hypothetical state with 60% blue voters and 40% red voters, and three different ways of proportioning it out. So number one is perfect representation, where you have 5 districts, 3 are blue, 2 are red, and the outcome is proportional. Number 2 demonstrates a compact but unfair gerrymander, where the red voters are cracked into 5 different districts so that they can't ever actually get a majority, and blue wins 2 more districts than they are entitled to. And then the final one is neither compact nor fair, where red engages in both packing and cracking to create a hypermajority in one and disperse votes in several others so that they can get 3 red districts, even though they should only be entitled to 2. So previously in the literature, this issue has been approached a variety of different ways, generally at the state partisan level. Ours is a little bit different as we're looking at the state individual level. 2 previous metrics include the efficiency gap and the seats votes curve, both of which consider the concept of wasted votes. However, they do have some flaws in several surprisingly common edge cases. Additionally, there's been some research done at Duke, actually, on Monte Carlo Markov chains to evaluate the probability of gerrymandering, the Mattingly group. And there's a team out of Haverford that utilized automated redistricting using Bernoulli tessellation and other clustering and optimization algorithms. Though both of those focus on the likelihood of maps and creating fair and relatively compact districts without considering electoral data. So our approach is different because we were focusing primarily at the statewide level on individual people. The rationale for this being that previously, when the courts have ruled on the issue of gerrymandering, they've wanted to see demonstrable harm against individual voters in the form of justified complaints. That is, if I am the voter and I feel like I've been gerrymandered, I can present a comparator map which shows me living in a district where I am not gerrymandered without gerrymandering other individuals. We have approached this by creating a metric to calculate the number of gerrymandered people, and then we have an algorithm that utilizes simulated annealing and local swaps to reduce this metric to ideally a global minimum. So more specifically on our metric, we grab 1,000 good comparator maps generated by MCMC methods such as JerryChain, which is an open source project. And then we divide the voters into one of 2 groups, packed or cracked. Cracked voters are individuals who did not win in their current map, but can be demonstrably proven to have won in other fair comparator maps. And packed voters are individuals who win their current map and can be shown to win in other maps, albeit with a margin of victory of at least 5 points less. This final metric is then added together and averaged over all 1,000 comparator maps to create our gerrymandering score for the map in question.
So to look at how different maps fare according to our gerrymandering score, these 2 maps are official districtings used in 2012 and 2016. We can see that the 2012 map fares worse according to our metric. They have more people gerrymandered, which makes sense given that this was a map that was struck down by the courts for the unfair gerrymandering that was occurring. These 2 maps are not official maps. The first is a bipartisan map drawn by a panel of 10 retired North Carolina judges. The second is actually drawn by an algorithm developed by the group from Haverford in a paper called Automated Congressional Redistricting. So neither of these maps take electoral data into consideration in the process of generating the maps, but they're both trying to keep districts contiguous and relatively compact with approximately equal populations. So when it comes to applying our swapping algorithm, we take in an original map, and then our algorithm swaps voting tabulation districts on the district borders to minimize our gerrymandering metric. VTDs, there are 2,690 in North Carolina. They're the smallest level of collected electoral data in the US. So in terms of our swapping algorithm, we have 3 legally required constraints. We try to maintain compactness and population deviations within certain bounds, and then we try to maintain contiguity throughout all of our districts, regardless of our swaps. So the next question then becomes, how do we pick swaps? We have 2 implementations of this. The first is a stochastic and greedy approach. So we randomly select candidates to test, and then we accept the first good downhill swap. So in this case, we never allow our gerrymandering score to increase in the process of our swapping. The second approach we took is a simulated annealing approach. So here we're also randomly selecting candidates to test, but occasionally we do accept a bad uphill swap based on a certain probability that we calculate. So the goal for allowing these bad uphill swaps occasionally is to escape early local optima to try to better approach a global optimum. So that calculation for the probability of accepting a bad swap is based on a couple different parameters, one of which is the temperature. So the start temp is the starting temperature, and the higher it is, the higher the probability of accepting a bad swap is in the beginning. And then for every L swaps that we make, we decrease that temperature based on temp factor, thus reducing the probability of accepting bad swaps as we go along. So to look at swapping in action, this is a version of the simulated annealing algorithm specifically aimed to reduce packing on single districts. So not precisely what's happening in our gerrymandering metric as a whole, but a good way to take a visualization of what might be happening under the hood. So these are districts 3 and 4 from the 2016 official map. The pink is the original districting, the blue overlay, the newly swapped district. And as we can see, while keeping the compactness relatively close, we're able to sort of decrease the margin of victory. So the winning party for each district is winning by a smaller margin and therefore is less packed.
Right. So here's a demonstration of what happens after we run the full algorithm on one of the initial starting maps. In this case, we chose the 2016 official North Carolina map, and we initialize our parameters, start temp, temp factor, and compactness deviation with 800, and as the values given on the slide. And these are the results that we achieved. As you can see, that there's been quite a bit of change in the map visually, and other than that, the most important figure, which is the gerrymandering score reduction, we have found to go down from 1.15 million to 571,000 in our modified map after we apply the algorithm, and some values for the original compactness and the original average compactness and the worst compactness in the original map versus the new map. So some further data, further visuals on how it looks in terms of the partisan breakdown of the map after we run our algorithm. So as you can see, this map indicates that districts 1, 4, and 12 are the Democratic districts in the 2016 elections. And after we apply our algorithm, we're able to kind of decrease the bluish hue here to indicate that it has a less partisan lean in our modified map, in our new map, which is supposed to indicate that instances of democratic hacking has been virtually reduced. And the algorithm might go as far as even flip a district. For example, District 2 is won by the Republican Party in the original 2016 map, but in the new map, it's won by a Democratic Party. So yeah, our algorithm can cause a substantial reduction in the margin of victory in individual districts. Further visuals to clarify what exactly the notions of cracking and packing look like after we have run our algorithm on the states. So in the original case, districts 1, 4, and 12, indicated by the heavy concentration of charcoal to be largely instances of large democratic packing. And after we run our algorithm, we have virtually eliminated this kind of packing in our new map. Although we do see some instances by the orange, indicated by the orange in the new map of democratic cracking still to be present in the new map, we do believe it is quite a minimum level, and we do have a decrease of democratic cracking nonetheless anyway in the new map. So we believe this is a good performance from our algorithm.
Yeah, and so these are the same heat maps, but instead for packing and cracking of Republicans. So as you can see in the original map, there were quite a few districts where Republicans were actually packed a bit, but in the new map, for the most part, they aren't packed at all. And counterintuitively, Republican cracking actually seems to go up a bit in the new map, especially in the Charlotte area and the original districts 1 and 4 area. But ultimately, however, considering the big decrease in Democratic gerrymandering, it's most likely that this increase in Republican cracking was a side effect of that. Overall, however, we can see the overall effect of this algorithm has been a pretty significant decrease in both packing and cracking. So we tested different parameters for our simulated annealing algorithm, mainly temp factor and start temp. So in one try, we kept temp factor constant and we changed the value of start temp. And we found that a start temp of around 400 did the best, but a start temp of 600 did around the same as well. However, do note that the runtime increases considerably when we increase the start temp. So we also, prior to this, we've always been running initializing with different starting maps. Or rather, prior to this, we've always been using the 2016 map, but now we tried running our algorithm with different starting maps. So the top row is the ACR map, which you can see is actually quite favorable to Democrats with 7 Democratic districts. But after running the algorithm on it, the score decreased by about 33%, and the districts are a bit less Democratic. Same goes for the bottom, which is the bipartisan judges map. We lowered the gerrymandering score by about 25% in this case. So what are our future directions? Obviously, there's lots of room to further optimize our simulated annealing hyperparameters. One other big thing we might want to do is integrate compactness into the cost function of our simulated annealing. Right now, we have compactness as a hard constraint that can deviate by no more than around 5 or 10%, depending on what we set. But if we integrate that into the cost function, that allows us, initially at high temperatures, to choose swaps which drastically change compactness, but at low temperatures to gradually converge and pick only swaps that increase compactness. What this means is that the algorithm can further explore a wider array of swapping options and a wider array of districts, so that ultimately we might change the map in a more drastic manner and find a true global optimum. In our current districtings, our swaps and our final districts are always variations that still look pretty similar to our original maps. We also can analyze how our algorithm affects competitiveness and communities of interest, factors which aren't directly optimized for, but which can be changed by our algorithm. We'd also like to apply our algorithm to more states and utilize parallel processing and other computational techniques to increase runtime performance and speed. But other than that, thank you so much for watching our presentation. We hope you enjoyed it.